Today we're going to start chapter 15. The remainder of this course is going to be basically review and small extensions of topics that we saw last year in our Algebra 2 course, so that's good news. Chapter 15 is going to be dealing with exponential, logistic, and logarithmic functions. Last year we talked about exponential and logarithmic functions, so that part should be relatively familiar still. We didn't talk about logistic functions, but they're not that big of a deal. They're relatively straightforward, and there's not that much about them, so that'll be new. But this is a good topic, I think, to review, because in my many years of teaching the Algebra 2 course, the single least retained topic from Algebra 2 is logarithms. So getting a second pass through that, I think, will be good for everybody. Okie doke. All right, let's get moving on this. All right, so let's start just by talking about exponential functions. So exponential functions are of the form f of x is equal to a times b to the x, with the constraints that a is not 0, b is positive, and not equal to 1. Let's take a moment and just kind of discuss why we have all these additional constraints here. So what would happen if a was 0? Lily? Right, so we'd end up with like f of x equals 0, which is a constant function. We've already described constant functions as like that's a special linear function, so should not be considered exponential. That's why a isn't 0. What would happen if b was 1? Lily?
It wouldn't be exponential, it would just be linear.
Yeah, so if b was 1 to the any power is still just 1. 1 times a is a, so you have f of x equals a, another constant function, not what we're interested in. What would happen if b is negative? Why are we staying away from that? What would be the problem if b was negative? This one's a little tougher to see. Lily?
Wouldn't it be up and down? It would not be exponential, but it'd be...
So yeah, one situation is like it'd be jumping, the points would be jumping back and forth across the x-axis. That's one reason. Another issue, your inputs for x can be anything, right? Specifically, they could include things like 1/2, 1/4, 1/6, 1/8. Why would that be a problem if b was negative? Remember that those are all equivalent to radicals. Like exponent of 1/2 is the same thing as a square root. 1/4 is a 4th root. 1/6 is a 6th root, etc. And if you take an even root of a negative number, what do we get? Imaginary result. So this thing is would have discontinuities all over the place because you'd keep getting those imaginary results. So you'd have just a tremendously poorly behaving function here that's discontinuous, like infinitely many places, jumping back and forth across the x and y axis all over the place, and would be just like a miserable, miserable function to try to cope with. Definitely not what we want to include. Does everybody feel cool with that? A little bit of vocabulary here. The a, oftentimes we refer to as the initial value. The reason we say that is because if we think of x equals 0 as our very first input, we'd end up with a times b to the 0. And what does b to the 0 equal? 1. Again, we should remember that any non-zero number to the 0 is equal to 1. 0 to the 0 is indeterminate. It's undefined because depending on how you look at it, it might be 1 or it might be 0. We can't agree, so there's no answer to that question. And then obviously 1 times a is just a, right? So that's why we sometimes will refer to that as the initial value. Feel good there? The b we refer to as the base of the exponential. So let's just do some little basic easy review. So let's say we want to evaluate for the function f of x equals -2 times 4 to the x. Some things like f of 2. So the first thing I want to ask you, -2 times 4 to the x, can I write that as -8 to the x? No way, Jose. Right? Why not? Well, if you remember, there's 2 ways that we can multiply numbers together. So if the bases are the same, we can multiply them by keeping the base the same and adding the exponents. Or if the exponent is the same, we can multiply the bases and keep the exponent the same. So if I look at -2 times 4 to the x, the bases are different and the exponent is different. So we definitely can't multiply those 2 things together. Everybody cool with the reasoning there? Most of what we're going to be doing right now is just a good excuse for me to review some of these properties of exponents, which ideally we remember perfectly, but it's been a year, so they drift. That's the point of doing this again, is an excuse to review things. All right, so if I do f of 2, all I'm basically doing is plugging 2 in for x. So the first thing I should do there is the exponent, so 4 squared is 16. And 16 times -2 is -32. Everybody happy there? F of 0, what's that going to be? Quick in your head. -2. Why? Yeah, it's the initial value, right? Yeah, just like the explanation we gave above, right? Everybody's cool with that? If you're not, don't be shy. Just go ahead and speak up. You know, I'm going quick because a lot of this is kind of reviewy, but if I have f of -3, well, we plug -3 in for x. And then what does a negative exponent mean? Yeah, it makes a reciprocal. Yeah, so that's really 1 over 4 to the third. And 4 to the third is 64. So that's going to be -1 over 32. And again, as we go through and hit these properties of exponents, I'm just kind of writing them there in blue off to the side, just as a reminder. Everybody's cool with what I'm doing? If you're not, holler at me. Okay, so if I do f of 1/2, that's going to be -2 times 4 to the 1/2. What does a fractional exponent mean? So radical, yep, a root. Specifically in this case, it's a square root. Okay, our last example here, -3/2. So the trick here that I'm going to use is I'm going to think about -3/2 as -3 times 1/2. And the reason I'm going to think about it that way is so that I can use this exponent of an exponent property. And think about it that way. Everybody cool with how I did that? So now this becomes relatively easy. For the 1/2 we've already done. That's just 2. 2 to the -3 is 1/2 cubed, or 8. And then I just multiply them together to get -1/4. Now, just as to just clarify here, all these problems we just did, you could just type these into your calculator as well, right? There's nothing wrong with doing it that way. We were doing them by hand as a good excuse to review these properties of exponents because it's been a minute since we've used them, and that's the point of like doing this again, is to review these things, right? Let's look at some more examples here. So let's say we wanted to write an exponential function from a set of points. Come here, where's my thingy? Make that a little bigger. Straighten that out. Ew, that's yucky looking. Okay. Table below gives the values for an exponential function g of x. Find the equation for that function. So what we're asking for is some g of x function, a times b to the x, right? So there's an easy way to do this and a hard way to do this, depending on the points you're given. To unlock the easy way to do this, we need the point whose x-coordinate is 0. Why? Because that automatically gives me the value for a. Everybody's cool with that? Then I can take any other point. My choice would be this one, because it makes an exponent of b to the first, which is the easiest one to solve for. And now we can just solve for b. So now that we have our values for a and b, we can put it back together again, and there's our answer. Easy, right? No big deal there. We cool? Any feedback from you guys is always appreciated when I ask stuff like that. Or you can continue to ignore me. That's okay too, I guess. Okay. Now, Mr. Kulik, you said there's an easy way and a hard way. Can we see one where we have to do it the hard way? Yeah, for sure. That's next up. So how do I know that this is going to be the hard way? None of the x coordinates are 0. Okay. So still the same goal. I need a equation a times b to the x. I don't have anything to get me the a for free, so what I'm going to do is I'm just going to end up creating a system of 2 equations using the 2 points that I'm given. I'll refer to those 2 equations as a and b. Recall last year in your Algebra 2 class, we would have talked about solving systems of equations. You remember the 2 algebraic methods we talk about for solving systems? Substitution and elimination. Either one of those is appropriate to use in this context. Personally, I like to use elimination. That's what I'm going to use here. Now, a little bit different in how elimination is going to work in this case. Last year when we used elimination to solve systems, we always had equations where the variables were being added or subtracted from one another. Here we notice that our variables are being multiplied to one another. So instead of using addition and subtraction to eliminate a variable, we're going to be using division to eliminate a variable. So the question here is, should I do a divided by b or b divided by a? The answer is it doesn't really matter, but you can make your life a little bit easier if you use the bigger exponent as the numerator, which is what I'm going to choose to do. So b divided by a is going to give me 12 over 48 equal to a times b to the negative 1 over a times b to the negative 3. Feel good so far? 12 over 48 reduces to 4. The a's will eliminate. And then to simplify the b's, I'm going to do b to the negative 1 minus a negative 3, which is b squared. Again, the rule we're using there is that rule of exponents, right? When you divide, you're subtracting the exponents. So far, so good? To get that b by itself, what am I going to have to do? Right now I have a b squared. I want just b, so square root both sides. Very good. Remember, because we're doing it to both sides, we're generating a plus or minus by doing that. But remember the restrictions we have on b. What does b have to be? Positive. So that plus or minus, I can immediately drop. So there's my value for b. Once I have that, I can then substitute that back into one of the 2 equations. I'm going to sub it into equation b. It doesn't really matter which one. I usually go with whichever one has the more convenient exponent. Again, a negative exponent makes a reciprocal. So I divide both sides by 2. There's my value for a. There we go. little bit worse, but not so bad, right? Still not too bad. Everybody doing okay so far? All right. So the next idea we want to talk about, so we have these exponential functions, right? Let's say that I have two different ones. If I want to compare them, this is not often super obvious what to do. If the bases for the exponentials are different, that tends to be the biggest predictor. What we'd like to be able to do is to rewrite these exponentials so that they have the same base. The question in doing that is, okay, I want to rewrite them to have the same base. What number should I pick to be the common base? Well, one of our canonical choices is what's called the natural base, or Euler's number. Again, we would have talked about this last year. The symbol we use to abbreviate this number is the letter E, the lowercase letter e. This lowercase letter e is the limit as x approaches infinity of 1 plus 1 over x to the x, and it's equal to the irrational number 2.7182818, yada, yada, yada. So that's an irrational number. What does irrational mean again? Doesn't end and doesn't repeat. Or equivalently, just you can't write it as a fraction. Those two statements are equivalent. So what we're going to say then is some exponential function f of x equals a times b to the x can be written, let's say, can also be written f of x equals a times e to the kx, where a is not 0 and k is not 0. Now notice here that we haven't included how we're going to do this transformation, simply that we can do it. We'll talk about how we do it later. The takeaway here, though, is that if those two things are equivalent, b is going to have to equal e to the k. Everybody feel cool with that? So that's the big takeaway right there, is that essentially e to the k is going to be the base of our exponential. Everybody see that? Okay. So we'll circle back to this idea and talk about how we actually do this transformation later, but we need to build out a little bit more stuff before we're ready to do that. So when we talk about these exponential functions, we really classify them into two types. One type we talk about is exponential growth, and the other type we talk about is exponential decay. And we can tell if it's going to be exponential growth or decay just by looking at the equation. So in our classical sense, our classical equation, we know that if b is greater than, let's be specific. if A is greater than 0 and B is greater than 1, that would imply it's going to be growth. And then for decay, A would be positive, and then B would be between 0 and 1. For the new version that involves this letter E, the growth is going to be A is greater than 0 and K is greater than 0. And decay is going to be A greater than 0, but K less than 0. Grab that door. Seems like it's about that time. And then what would happen if A was less than 0? Just the criteria switch, right? Does that feel okay? Yes, Eddie?
What exactly did you write in red again? What does that mean? If they were
So the first is if the A is positive. If the A is negative, just the criteria is switching, right?
Yeah.
This, you know what I'm saying?
Yeah.
That's all that we're doing in red. So that's just some definition. Let's look at another example now. That's not what I wanted. There we go. Okay. So it says, given that a population of a certain city in 1990 is 782,248 people, and the population of the same city in 2000 is 895,193 people, and assuming the population growth is exponential, in what year will the population reach 1 million people? So when I read this, it really sounds like two questions to me. The first part reads like I'm going to have to write my exponential model for the situation. Hi, what's up?
Grab the box.
Yeah, go ahead.
Thank you.
And the second part of my question then is going to ask to solve that model for some specific value. Do you guys kind of see that?
Thank you. Have a nice break.
You too. Make sure you wear your sunscreen.
Why, thank you.
All right. So if I read this, probably the natural thing to think would be, well, I'm going to write a function for our exponential function that looks like this, where x is going to be the year and f of x is the population. So I'd be using the points 1990, comma, 782, 248, and 2000, comma, 895, 193. Does anybody notice a little hiccup here? You got to kind of do that harder process to write the model because I don't have a point with the x-coordinate of 0. So one thing I can do to make this problem easier on myself is instead of thinking about the independent variable as the year, if I think about it as the years after 1990, that would change the points into 0 782,248, and then 10, 895,193. Oops. And that makes life a little bit more convenient for us, right? Because instantly we get that the A is 782,248. Everybody cool? Okay, so let's do that. So we still need to solve for the B though. So let's plug in our other point. That look good to you guys? To solve for B, what should I do first? It's not a trick question. Yes. Yeah, because of the 10 there. Yeah, divide by the 782,000, right? Very good. Okay, and then how do I get rid of the exponent 10? Not a log, the 10th root. So again, the logs are if the variable's in the exponent. Again, since that's an even root, I need a plus or minus, but because we're solving for B, I know that it has to be positive, so I'll just cross that out. So typing this into my calculator, to get the 10th root, I can type in the number 10. And then if I press the math button and choose option 5, that allows me to pick any root that I want. Alternatively, how else could I do the 10th root? Very good. I could use the exponent 1 over 10. So I do that. So there's my value for B. Let's do that real quick so it's easier to read that. So is this a growth or decay model? Is this going to be exponential growth or decay? Growth, right? How can I tell? A is positive and B is greater than 1. How else could I have told even before that? I looked at the 2 points and the population went up over time, right? Okay, so what we have then, f of t equals 782,248 times 101,357,8108 to the t. So this first part that we've done here is just like the first part of the problem that I had highlighted in yellow. Okay. So to finish the second part, then I need to find the year, the time, when the population gets to 1 million. So this is the equation we're solving. Now, algebraically to solve this, what are we going to have to use? To solve this algebraically, what are we going to have to use? Since the variable's in the exponent, we'd be having to use a log. Have we talked about logs yet? Do you suppose I'm going to bust out a logarithm right now to solve a problem that I haven't introduced how logarithms even work yet? No. How else could I do this problem if I'm not going to do it algebraically? Graphically. So I'm going to use the calculator to do this graphically. So the left-hand side of the equation, I'm going to type in the 1 million into y1. The right-hand side of the equation, I'm going to type in the other piece. Rather than typing in that whole long decimal, though, what I'm going to do is I'm going to store that decimal into the letter A. And not only does it store the decimal points I can see, but it also stores like the 99 other decimal points the calculator has in the memory that I can't see. So it's going to give me like a really precise value, which I'm super excited about. Everybody feel okay with what I did there? So that's just a calculator trick to help get me a nicer answer without having to type a bunch of googly-gocks in. Okay, before I go anywhere though, I'm going to reset my window. So remember here, my x variable in my calculator is representing the t in my equation, which is the years after 1990. The first year after 1990 that I care about is 0. That makes for a good lower bound. 10 years after, my population's gone up about 100,000. 20 years after, I'm going to estimate the population's probably going to go up about another 100,000. So I'm guessing that my answer is going to be somewhere around 20, but I'm always going to overestimate because as long as I can see the intersection, I'm good. If I can't see the intersection, I'm going to have to go back and change my window again. I'd rather overestimate than underestimate there. Is everybody okay with that? Okay. The y's are representing my population. The smallest y that I care about is this 782,248. That's awfully specific. I think I'll probably just round that down to 750,000. So it's an even, nice, round, neat number. The biggest population I care about is the 1 million. But again, I'm going to make that a little bit bigger so I can see the intersection easily. So I'm going to make that 1.25 million. So let's hit the graph button then. Here's my line for 1 million. Here's my population curve. There's my point of intersection that I care about. How do I find the point of intersection on my calculator? Second trace. The command I'm looking for is intersect. Since there's only 2 curves and 1 intersection, I can just press enter 3 times and I get 18.2. What unit should I write here? Years after 1990. Very good. So let's go back and make sure that this actually answers the question, though. In green, it says, in what year will the population reach 1 million people? What would I write here? I would say during 2018. You guys agree with that? Oh, 2008, sorry. Yeah, arithmetic. Thank you. During 2008. Everybody agree? Okay. So that feels good there. All right. Now, here's my question. Does an exponential function seem like a reasonable way to describe the population of a city? So let's say that we go, to the year 2200. So that's going to be 210 years after 1990. According to our model, the population of the city is now 13,284,000. That seem kind of fishy to anybody else? Why would that be potentially problematic? What's that? Probably doesn't reflect real life, right? There's very few instances where a city's gone from like 700,000 and 200 years later it's going to be 13 million. That's a heck of a lot of increase. Why do you think that's going to be? Why do you think that seems like too much? What are the constraints that limit the size that your city could be? space, right? There's a geographical area that defines like the size of your city. Now you can build up, but like that's pretty expensive, and it better be a good reason that you want to build up. Like New York City, we built up, and you have a big, huge, dense city, but there's not a lot of cities like that. Work, so there has to be a reason for those people to be there. And other resources in general, right? There's finitely many resources. Your city can't get infinitely big because eventually you're going to run out of stuff. Everybody agree with that? So what would be a little bit better of a model would be something that has like a built-in upper bound to it that still kind of grows exponentially in between. We have a type of function that does that. It's called a logistic function. Okay, so we have these two logistic functions, or two versions of the same logistic function. Notice these parts are basically just exponential pieces, right? Everybody see that? Yes, sir. That is e to the negative kx, yes. No. So this is different. Absolutely. Very good eye. So the key feature here for our logistic function is we have a horizontal asymptote at y equals 0 still, and another one at y equals c. So we have a lower bound on our function, and now we also have an upper bound on our function. Sometimes we call this upper bound the limit to growth. So like how big your, like how big your function could actually get is bounded on the top by that horizontal asymptote. That's pretty neat. Just like your exponential functions, there's two types of logistic. You have logistic growth and logistic decay. The rules, however, are opposite for the B's. So logistic growth is going to happen between 0 and 1, and decay when it's bigger than 1. But for the other version, the rule is the same. So logistic growth when k is greater than 0, and decay when k is less than 0. The reason that that's not flipped for the version with the e in it is because we have that negative sign built into the k. So that's why we put the negative sign in the formula there, John, is so that the growth and decay criteria match the exponential growth and decay criteria, and it's not flipped like it is for the other version. Is everybody okay with that? So what is this going to look like? Well, you're going to have your upper bound at y equals c, and your lower bound at y equals 0. And your growth would look like this, and a decay would look like that. Everybody's cool? So let's just do a couple of like simple examples here to get our feel around the notation involving these logistics. Okay, so it says graph the following on your calculator, find the y-intercepts and equations for the horizontal asymptotes. I'm going to do the graphing part all at the end so that I'm not toggling back and forth between the two screens. We're going to do the y-intercepts and asymptotes first for both of these, then we'll graph both of them at the same time. Sound good? Okay. The y-intercept here, the y-intercept always occurs at what x-coordinate? 0, right? So I'm just going to find f of 0. So 0.6 to the 0 is 1. 1 times 3 is 3. 1 plus 3 is 4. So I have 10 over 4, or 2.5. Everybody's cool there? Horizontal asymptotes. One of them, the lower bound, is always y equals 0. The upper bound is y equals c, which in this case is 10, right? Just the numerator. So again, we were y equals c, which is just the numerator. Bonus question, is this growth or decay? This is growth. Since the b value is 0.6, that's between 0 and 1. So just that was a bonus question there for us. Okay. So again, for part B, the y-intercept, we just care at f of, or when x is 0. So e to the 0 is 1. 1 times 4 is 4. 1 plus 5 is 1 plus 4 is 5. So I have 31 over 5, or 6.2. What are my horizontal asymptotes at? Anybody? 0 and 31, very good. Always 0, and then the value for c, which is just the numerator. And then is this growth or decay? What's the value for k in this case? That's going to be the thing that tells us. The k here is 2, right? Not -2. Remember that the negative sign, as John so clearly pointed out with his observance, was part of the formula. So based on our criteria, since the k is positive, this should be logistic growth. All right, let's type these into the calculator and take a peep at them. So I'm definitely using the fraction command to type this in because Well, it's going to be kind of a mess of parentheses without it. So there's the first one. Remember to get the E button on your calculator. You press second and then the LN button, which is just a few up from the on. So there's my two functions. I'm going to reset the window because remember the last window we used was like super customized to a problem with some real big numbers in it. So I'm going to reset my window to go from, say, -10 to 10 on the X. And then the Y, the lower bound for each of them is 0. So that looks good. The biggest upper bound is 31. And I don't know, by 5 sounds good. That sound good to you guys? All right, let's hit graph. Here's my first logistic growth. Notice it's increasing from left to right, but it seems capped at 10 there. This second one is my second logistic growth. Again, it's increasing from left to right, then seems capped at 31 there at the top. This seems like a pretty nice modeler for a population growth problem, right? Once you get to the carrying capacity of whatever your system is, probably not going to grow much past that. So let's take another one of these population problems, and instead of doing it as a exponential problem, let's do it as a logistic problem. And this will be the last example that I have for you guys today. All right. The population of a city can be modeled using a logistic growth equation, yada, 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 where P is the population in the city T years after 1950. At the beginning of what year will the city have 1 million people? Well, notice here the model's already been made for us. That would be the case. I would not be expecting you to come up with your own logistic model on your own. So essentially, we're being asked to solve for what year. So we want a value for T. And our input's going to be 1 million that we're plugging into the population. Everybody feel cool with that? So the equation we're going to look to solve is this one. So, calc time. So I'm going to type the left-hand side into Y1. And I'm going to type the right-hand side into Y2. Just as a aside here, while I'm typing these things in, it's worth mentioning this method that we're using of solving by graphing is a really useful one, particularly if you're taking like a standardized test and you're not sure how to algebraically solve something. So if you have an ACT or something and you don't know how to solve something, if you graph the right-hand side and the left-hand side and just look for the intersections, that should do it, presuming that the solutions are real numbered. Perfectly reasonable method of solving something where you can get away with not actually knowing algebraically how to solve it, but let your calculator do most of the heavy lifting for you. So if you get stumped on something on like an ACT or whatever, that's a good trick to keep in mind. All right, so I got that typed in. I'm going to go ahead and reset my window. So again, the X is representing the T here, which are the years after 1950. So year 0 seems like a good minimum. I don't have a good intuition as to how long this is going to take. I'm just going to guess 100. I can always go back and make it bigger, I suppose, if it's not big enough. But the minimum Well, for this logistic function, what's the lower bound got to be? Always 0. So I'll leave that as my y min. What's the upper bound for this logistic function have to be? Great. The value for C, 1,425,000 and yada, yada, yada. That's an awfully specific number. I'm just going to do 1.5 million because, you know, it's like just a rounder number. And we'll go up by 100,000s there. So I'll hit graph, take a look. Here's my 1 million line. Here's my logistic growth curve. Is it going to get it? Barely squeaked it in. What would happen if I couldn't see the intersection? Just go back and make that x range bigger, right? You should have no problem getting in between the y's. But we'll just go back and make that x range a little bit wider. Find the intersection then, second trace, intersect command, enter, enter, enter. So I get about 79,002. Again, remember that T is the years after 1950. So, does that actually answer the question that we're being asked, though? Remember, the question we're being asked is at the beginning of what year? So how would I answer this then? 2029 is what John says. Does everybody agree with him? I don't. I would say it should be 2030. Because at the beginning of 2029, you're not going to be at 1 million people. You're going to be just shy of 1 million people. The first year at January 1, midnight, that you're going to be at 1 million people is in 2030. Somebody last hour said that the 0.02 or whatever there would be 5 o'clock on the first day of 2029 is like, that's how. But the question asked, the beginning of what year? That would be midnight, January 1, or midnight 01 or whatever. So that's what we got. Should be 2030. Sneaky. On the, even though it's that little, the standard rounding would say round down. In the context of this question, it's no matter what is a round upper. This feels like a good stopping point. At this point, you guys should be able to do 1 through 16. Notice the problem set is due on May 1st, juniors. So you don't have anything to do this Sunday. You don't have anything to do next Sunday. You don't have to do anything the Sunday after that. So enjoy your vacation. Don't forget about this, but it's not due till the week after we come back. So you'll have plenty of time to remind yourself to do this. Or you could do it before you leave. That's fine too. I don't know. Maybe you're that kind of person that's just like, I need to get it done.